so we can start for the day. So our first speaker for the day is Iryna Egorova, who's going to tell us about the Toda shock and rarefaction problems. So Iryna, the stage is yours.
Thank you for presenting me. Of course, I would like to thank organizer for inviting me to participate in such a nice and motivating event. And I'll present some recent results obtained in collaboration with my colleagues Iryna, Michor and G Teschl from Vienna University. I'll talk about the long-time asymptotics of step-like Toda lattice solutions. That is about Toda shock and rarefaction problems. Here is the Toda lattice in Flaschka variables, and initially the Toda shock and rarefaction problem were associated with such type of initial pure step initial data, where the case of negative B corresponds to the shock problem and positive to the rarefaction one. On a physical level of rigor, qualitatively, the behavior of such solutions is well understood. For example, for the shock wave, it is known after the work of Bloch and Kadama, who used the rhythm modulation theory, and after the work of Inakidis Dave Bach, who used Lax-Livermore approach, it is known that there are two regions where the solution is asymptotically close to a modulated finite gap solution, and in the middle region, the solution is asymptotically close to a periodic solution of period 2. However, these results were not fully rigorous, and recently Percy Dave listed the Toda shock problem among open problems of the theory of integral system and proposed to study it by use of nonlinear steepest descent. Motivated by this idea, we implement rigorous asymptotic analysis for arbitrary, say, general step-like initial data, which tend to different constant backgrounds on different half-axes in a way that the perturbations decay or polynomially or exponentially fast. And we intend to present exact asymptotics in all principal regions of space-time half-plane and justify them. And one has to mention that a proper statement of Riemann-Hilbert problem appeared already in this work. The authors study the rarefaction wave, the transition region. They described asymptotics in this transition region. And the case of one and the same constant background, that is a decaying case, is analyzed rigorously, also by use of nonlinear steepest descent by Kruger and Teschl and Billman and Rockton. Okay, let's dwell briefly on basics on inverse scattering transform method for the Toda lattice. The space Lax operator here is the Jacobi operator, and for the Jacobi operator with step-like coefficient, the direct inverse scattering theory is very well developed, not only on the constant backgrounds, but also on the finite gap ones. And in particular, it is known, it is proved that if the initial data satisfy such a condition at the moment t equal to 0, then the solution of the Toda lattice exists, unique, and belongs to the same class. One has to say that for KDV in the framework of inverse scattering transform, this is not true. There are losses in the number of moments and derivatives. Okay, from the fact that we listed here, it is clear that whatever Riemann-Hilbert problem we choose, it will be always solvable. Perhaps the solution will not be unique. And now we restrict ourselves only with the case of non-overlapping spectra of backgrounds. And without loss of generality, just by shifting and scaling of spectral parameter, we can assume that our right background is simply the free Laplacian, that is, the spectrum is located on the interval -1, 1. So we have the operator, underlying Jacobi operator, with the spectrum on the union of two intervals. This is the spectrum of multiplicity 1 and a finite discrete spectrum. The spectral Jacobi equation has two-use solution, which are normalized as free exponent of the background operators, where Z and zeta are Joukowsky transformation of the initial spectral parameter lambda. Both your solutions are well defined in this domain on Z plane with a cut along the image of the left background spectrum. Okay, the Wronskian of two-use solution is an important characteristic in step-like problems because it yields a connection between the left and right transmission coefficient. The Wronskian can have zero values at the edges of continuous spectrum. In this case, we talk about the resonance at the point, at the end point of continuous spectrum. What is right scattering data? Say a minimal set which we need to reconstruct our step-like solution uniquely. This is the reflection coefficient, which is given on the right background spectrum, a function which is given by this formula on the left background spectrum. This function is just the product of the left and conjugated right transmission coefficients. And then also eigenvalues and normalizing constants. In the domain Q, which we introduced, let us introduce a vector function. Here T is time-dependent right reflection coefficient. This vector function will be meromorphic and with poles at the points of the discrete spectrum, and it has limits as lambda tend to infinity, that is Z to 0, and we finite limits. And we can obtain our step-like solution from these formulas shown here. But as you know, the Riemann-Hilbert problem is always parameterized by two parameters, space parameter and time parameter. And here, in fact, we have to consider two different Riemann-Hilbert problems to reconstruct our coefficient A of the solution. And sometimes if the oscillations are too fast, we cannot use this formula, apply this formula. Then we expand this product up to the second term and also obtain information about A coefficient. Now, having this vector given in this domain, let us extend it outside of this domain on the whole complex plane by such a formula, where sigma 1 is the first Pauli matrix. Then the obtained vector, the function, will naturally have jump on the contour with orientation as depicted here. And it turns out that this vector is the unique solution of the following Riemann-Hilbert problem. We seek a sectionally meromorphic vector valued function which satisfy the jump condition given here. It involves our minimal set of scattering data, and this is the so-called right space function, which is the key exponent of our jump matrix. Also, it satisfies the residue condition at poles, as usual, very important symmetry condition, the normalization condition, which is given in such a way. And if you compare the normalization condition, that one which appears in the KDV case, in the KDV case, we have exact values 1, 1 of the vector at infinity. And here we don't have exact values, only dependence between the components of the vector. And the last condition just describe us the behavior of the vector in the resonant on the non-resonant case. And as you see, the jump matrix in the resonant case has a singularity known from L2. However, we can prove uniqueness of the problem. And namely, this fact that we can easily prove the uniqueness of both initial and model Riemann-Hilbert problem, which appear later, that was the reason for choice of the vector statement of the Riemann-Hilbert problem. Another reason, which is also important, one has to say that in the shockwave case, the matrix model solution does not have invertible matrix solution with just L2 singularities for sufficiently large certain parameters of space and time. From the other side, if we choose the vector Riemann-Hilbert problem and we want to have a uniqueness, we should respect the symmetry condition. This is a key ingredient to ensure the uniqueness. And it means that for all transformation which we do which lead to the model Riemann-Hilbert problem, the deformation of contours should be symmetric. Also, there are some constraints on the appearance of solutions of some scalar Riemann-Hilbert problems. For example, this condition ensure the normalization condition, and also the symmetric condition require a special form of the Cauchy kernels. In our case, a proper choice is a matrix Cauchy kernel. Such a constraint, again, does not exist in the KDV case because the symmetry there is different. Let us now consider in more detail the Toda shock problem. Now, in a middle region, we don't have any more. This is a picture for the spectrum on these intervals, pure step initial data. In the middle, we don't have anymore the solution of period 2. It will be rather finite gap 1, gap quasi-periodic, but it can be periodic if the ratio of frequencies of quasi-momentum happen to be rational. In this case, we will have a periodic solution of this period. One has also to mention that we could make a statement of the Riemann-Hilbert problem by via the left scattering data. And in the step-like problems, it's often happens that the right choice of the Riemann-Hilbert problem simplify a lot further consideration. And for example, in this modulation region, we use the Riemann-Hilbert problem via the left scattering data. In what follows, we will call this region VDO region after Vinakidis Dave Tabar, and these are right and left modulation regions. Once our slow parameter psi is inside these regions, the jump matrix starts to grow on a part of the contour. And to get rid of this difficulty, we replace the initial phase function on a function with better properties. usually this function is called G function, and the transformation is G function transformation. To explain what is, to understand better what is the G function in our case, let us return to the spectral parameter lambda and consider the Riemann surface associated with this function. Let omega naught and omega be Abel differential of the second and third kind, normalized with by 0 A periods. Here A period is shown on the picture. Then their linear combination is again the Abel integral, also normalized. Moreover, the respective differential has such a structure. When both zeros of this differential are inside the gap, this function will be a good choice for the VDO region. One of them is always in the gap, and they move monotonously with respect to psi in this direction when psi grow, and when one of them reaches the end of the spectrum, we are not anymore in the VDO region. We step into the modulation region, and here we will need another G function. We allow the branch point of our Riemann surface now to move slowly, and the requirement on our Abel integral is that one of the zeros of this integral should coincide with the branch point. They move together. It turned out that this condition defines our point alpha of psi uniquely. It moves monotonously along the left background spectrum. And since this is the signature table of G function in terms of variable z, and this is the zero level line of function real part G is equal to 0, which shows that the jump matrix after our key transformation will be oscillating. And then we can start the standard process of upper, lower, lower, upper factorization of jump matrices, and then opening lenses. And the first step is, of course, to replace the pole condition on the additional jump condition around a small circle around the eigenvalue. And let us skip all this machinery. We will come to a Riemann-Hilbert problem, which is equivalent to the initial one, but now the unique solution of it is a sectionally holomorphic function, which has only weak singularities at the ends, some node points, say, and it solves, of course, it's symmetric and possess and satisfy the normalization condition, but it solves the jump problem on our contour, where the jump matrix is almost everywhere close to the unit matrix, except of this interval and small vicinities of stationary points of G function. And on the interval, the jump matrix is asymptotically close as t to infinity to a piecewise constant matrix, where this part of this matrix is just the jump of our G function. And this value came from an additional scalar Riemann-Hilbert problem, and namely this value contains an information about those scattering data which influence on the asymptotic in the right modulation region. What we see here, it's Blaschke product over the discrete spectrum, which is situated to the left of the bottom of the continuous spectrum. Some term which is connected with the resonant or non-resonant behavior of our jump matrix, and function chi, which belong to the set of minimal scattering data. And the vector model problem with this jump matrix has unique solution. A unique solution in a class of vectors with weak singularities, symmetric and satisfying the normalizing condition. There is a formula for it via the Jacobi theta function, but the appearance is quite cumbersome and uninformative, and I will skip it. An important question: how to compare the pre-limiting vector and limiting vector, which we found for which we found exact formula. This vector, they have jump on different contours, and we cannot compare them immediately, but instead we introduce such an error vector, where these matrices are the following. This matrix is just a solution of local parametrics problem, which was done in terms of Airy functions. And this matrix can be we can choose it in non-unique way. First of all, we have to admit poles for this matrix, and the requirement for it is first that the error vector should not have poles at the poles of this matrix. It should respect the symmetry condition for the error vector, and it should have such a connection with the unique solution of the model problem. And we constructed this matrix, and using the small norm arguments, we proved necessary equality, which allows us now to use the asymptotics from model vector to derive the asymptotics of our initial Riemann-Hilbert problem. To understand what are these asymptotics, let me show first what is one-gap solution. This is formula via the set of functions, and these values are just b periods of the respective Abel integrals. And in our case, all this object will be slow varying depending on the variable parameter xi. It means that on array, we still have finite gap solution. But in principle, this formula can be considered as modulated one-gap solution. And the result which is obtained is the following. Our step-like solution, which represents the shock problem, is asymptotically close to the one-gap solution, which we showed before. But for the A coefficient, unfortunately, the formula was obtained in such an average way because we could not compare two different Riemann-Hilbert problems. The oscillation were too fast. Now, a few words about the video origin. Here, the G function is just, is just the Abel integral, the exponent from the Baker-Kieser function, and assumes that the discrete spectrum is not empty in this region. Let us introduce parameter xi, which are defined when the zero line crosses the eigenvalue. Then our video region splits into disjoint sector. In each sector, the asymptotics will be the following one. This is ordinary finite gap solution with the spectrum, with the initial spectrum, and the phases are different in each sector, and the difference between these phases is given by this formula. Also, there is no local parametrics in this problem. That is why the error term here is exponentially small. And this picture demonstrates what happens if we have one soliton and the spectra of equal lengths. The change of phase leads to such a transformation for the solution. Okay, now about rarefaction problem. We also considered the respective Riemann-Hilbert problem. The local parametrics here is also found in Airy function, and the asymptotics are the following one. This function is an exact solution of the Toda lattice, linear one, and this is our rarefaction wave, and the solution is asymptotically close to this rarefaction wave in this way, uniformly in such a region, and the same is true in the other region. This is also exact solution of the Toda lattice. Last slide shows that, in fact, of course, the nonlinear steepest descent method is very powerful method which allows us to derive asymptotics everywhere. But in soliton region, perhaps it's better to use classical inverse scattering transform, because if we just allow our initial value to decay with such a speed, we can make a rigorous analysis of the Marchenko equation, and we derive that the solution is asymptotically close to the background plus solitons, which correspond to eigenvalues which are situated to the left of the interval. And also, you know, we don't have reflectionless or something like this in Marchenko equation because, for example, in our case, the reflection coefficient is modular equal to 1. So we always have the integral terms here, but one can rigorously analyze it, and this is all result, and to show that the solution splits into a train of so-called asymptotical solitons with one and the same amplitude and the moving phase. And and as a conclusion, I would like to say that it would be nice, first of all, to derive these asymptotics by use of nonlinear steepest descent method, and also that the methods which we used and that were developed, they allows us to apply them immediately to study the asymptotics on finite gap backgrounds. On the physical level of rigor, it was considered by Bigbayev, Novakshonov, and Sharipov for KdV equation, but we hope that one can do the same for the Toda lattice and derive exact asymptotics on finite gap backgrounds. And I think, thank you.
Thank you very much, Iryna. So if anybody has any questions, please feel free to either drop them in the chat or to unmute yourself and go ahead. May I ask a maybe silly question? So you are working with the first equation of the Toda hierarchy. Would it be possible to replicate your result or apply your method in the context of the reduction of the Toda lattice, where you just have even times? So that's called the Volterra lattice. I was wondering if you could just, what would you expect in such a context?
Sorry, even time, you said?
Yes, so if you go to the second equation of the hierarchy, and you look at the hierarchy where you just have even times, so you just start with the second equation, and you would just have the parameter b in that case. And I was wondering what would happen in that scenario if the same sort of method could be applied.
I don't know. I never worked with Toda hierarchy, and just one has to check. I don't know.
Okay.
Sorry.
Thanks. If I can see any hands raised, so if there aren't any other questions, of course there is the break. We're going to have breakout rooms, so I guess feel free to stop Iryna later on if you have questions. But in the meanwhile, I'd say